Guys, today we're going to go through an example of the Hungarian algorithm. This is a process that's used when you've got, say, a certain amount of tasks that need to be completed and a certain number of people or ways that you can get that task done. The Hungarian algorithm is used to try to allocate things to tasks so that the cost is a minimum usually, although sometimes it might be that we want to minimize the time. In this particular example, we're told we've got 4 workers, Andrew, Brian, Christine and Diana, who can complete 4 different jobs according to these costs. So, for example, Andrew will cost $30 if we get him to do job 1, $40 if we get him to do job 2, and so on. We're asked which job should be completed by each worker to make sure that the total cost is kept to a minimum. And we can do that using the Hungarian algorithm. So here we go. Step 1 is to represent the information in a matrix. So this is nice and easy because our table kind of resembles a matrix anyway. We're just setting up the matrix where the rows represent Andrew, Brian, Christine and Diana, and the columns represent job 1, job 2, job 3 and job 4. Step 2 is called row reduction. What we do here is find the smallest number in each row and subtract it from each value in the row. So in the first row, smallest value is 30, and what we're going to do is take away 30 from each of those numbers. So 30 take away 30 gives us 0, 40 take away 30 gives us 10, 50 take away 30 gives us 20, 60 take away 30 gives us 30. Once we've done that, we just move to the next row and repeat the process. Again, the smallest number in the second row is 30, so in this case we're subtracting 30 again from each number in the second row, and that will give us 40, 0, 10 and 40. Move to the third row, and by coincidence the smallest number in the third row is also 30, so we subtract 30 from each number in the third row, and we're left with 30, 20, 30 and 0. So you'll notice that each time we're creating at least one 0 when we do this. Smallest number in the last row is 20, so we subtract 20 from each value and we get 0, 60, 30 and 50 as our last row. So we've moved from this matrix down to this matrix, and that's where we're at the moment. Next step is to repeat the process that we just did, but using the columns as opposed to the rows. Now you'll notice that columns that already have zeros in it, we don't really need to do anything to them because subtracting 0 from each number is not going to achieve anything. So we basically just look for the columns where we don't have any zeros, and in this case that's the third column. We find the smallest number in the column and then subtract that value from each number in the column. So 10 is our smallest number, we're going to subtract 10 from each value in the third column, and 20, 10, 30, 30 becomes 10, 0, 20, 20. And that's where we're at the moment. Step 4 is the crossing out. So we do this step to kind of check whether or not we've kind of finished this process or not. What we try to do is cross out all the zeros in the matrix using as few lines as possible. So if you can see lines, either rows or columns where you've got multiple zeros, you would cross those out first because that's going to kind of knock out the most possible zeros. So we could start by wiping out 2 zeros there. Next one we can cross out is there, and we've got one more 0 to cross out, so we could do that way. And that's taken us 3 lines to cross out all the zeros in the table. Now a rule of thumb here is if the number of lines that we needed to cross out the zeros is the same as the number of jobs to allocate, then we're done and we go to step 7. If not, we have to go to step 5. So in this case we've got 4 jobs to allocate, 4 columns, and it only took us 3 lines to cross out, so we need to keep going and we go to step 5. So this is what we've got at the moment. Step 5 says that we look for the smallest number that isn't crossed out. In this case that's going to be 10. We subtract that value from all the values that are not crossed out, and we add that value to the numbers where the lines intersect. Okay, so the way this works is by picking our smallest uncrossed value, which is 10, we subtract it from all the other uncovered values. So 10, 10, 20, 20, 60, 20 becomes 0, 0, 10, 10, 50, 10. The intersections, we're going to add 10 to those values because 10 was our smallest number. So the two 40s here at our intersections are actually going to become 50s, and the rest of the numbers that were crossed out aren't going to change. So this is now our matrix. Alright, now we try crossing out again, and hopefully this time it will require us to use 4 lines to cross this out, because that'll mean we're done. Again, you cross out so that you can wipe out as many zeros as possible in one hit. So first row would be a good place to start. We cross that one out. Cross the second row out because that wipes out 2 more zeros, and you can see that it's going to take us at least 2 more lines to cross out these last 2 zeros. There's no way we can cross them out in one go, so it's now taken us 4 lines to cross out all the zeros, which means we're done with this, this part of the process, and we can go to step 7. If necessary, we might have had to repeat step 5 again until we could get enough zeros in the matrix. Alright, so allocating tasks. The zeros in each row basically represent the task that that person could complete. So person A, we could give them job 1, 2 or 3, because that's where the zeros are in their row. Person B can do job 2 or 3. Person C can do job 4, and person D can do job 1. Which is what we've just said there. So pretty clearly we're going to want person C to do job 4, that's the only option, and we're going to want to allocate person D to job 1. Okay, so those two we don't have a choice with. This graph here is a bipartite graph that just shows which jobs can be completed by each person, and that's sometimes handy to help you decide how to allocate the jobs. Alright, so in this case we're going to get 2 possible allocations. We said that person D must do job 1, and person C must do job 4. So C does job 4, D does job 1. Persons A and B need to complete the remaining jobs, which are jobs 2 and 3. They can both do job 2 and 3. So we could either make person A do job 2 and person B do job 3, or vice versa. We could make person A do job 3 and person B do job 2. So in this example there's 2 possible allocations that will give us the same minimum cost. If required, you might also need to work out what that minimum cost is, or if it was a time question, what that minimum time is. So to do that, we just go back to the original information that we were given in this table, and then use our allocation to work out how much this is going to cost us. So we said that Andrew, if we use the first allocation, we said that Andrew would do job 2, that cost $40, so 40. We said Brian's going to do job 3, that's going to cost $40. We said Christine's going to do job 4, that costs $30, and Diana's going to do job 1, which costs $20. So summing those costs together gives us a total cost of $130, and that will be the minimum cost for allocating these jobs.